Hello everyone, myself Soumya BJ, Assistant Professor, Department of ACE, SJBIT. In this session, I am discussing about the Module 5 topic of microwave and antennas. The Module 5 is related to the loop and horn antenna as well as antenna types. These are the topics that are to be discussed in this Module 5. In this session, I will be discussing about horn antennas. There are three basic types of horn antennas: E-plane sectoral horn antenna, H-plane sectoral horn antenna, and pyramidal horn. In the E-plane sectoral horn antenna, whatever deviation we do with respect to the horn will be done vertically in the E-field direction. Similarly, in the H-plane, we do the deviation with respect to the horizontal direction, and the pyramidal horn as deviation in both the vertical direction as well as in the horizontal direction, and the more dominant mode in this rectangular waveguide will be TE10 mode. Now let us understand the operation of these horn antennas. As we know, the electromagnetic wave propagation in the waveguide is different from that of the free space, and in the waveguide the propagation is restricted by the conducting walls and the waves will actually not spread. After reaching the mouth, the waves spread laterally and the wavefront becomes spherical. Therefore, at the mouth of the waveguide, there exists a near field region where the wavefront is a complicated one, and this is considered to be a transition region where the change of propagation from the waveguide to the free space takes place. And as the waveguide impedance and the free space impedance do not match, the walls of the waveguide are flared out, and this flared out structure we call it as a horn. Why basically we are using flaring is, in the transition region there is a change of propagation from waveguide to the free space, and since the waveguide impedance and free space impedance do not match, the walls of the waveguide will be flared out, and this flared out structure we call it as a horn. And this flaring is the one which provides impedance matching as well as more directivity and the narrow beam width. And the horn produces a uniform plane wavefront with a larger aperture in comparison to the waveguide. And as the aperture is large, the directivity is also high. As the aperture becomes more, the directivity also increases. Now coming to the design equations of the horn antenna. In the design equations, the theta is given by 2 tan inverse of d by 2l, and this can be written as 2 cos inverse of 1 by 1 plus tau, and L is given by d square by 8 tau. Half power beamwidth of optimum flared horns will be pi e is equal to 66 lambda by dE in degrees, and pi h equal to 67 lambda by dH in degrees. Here pi e is the off power beamwidth in E plane and pi h is the half power beamwidth in H plane, and dE is the aperture in E plane in free space wavelength, and dH is the aperture in H plane in free space wavelength. The directivity of this horn is given by capital D is equal to 7.5 AA by lambda square, and power gain Gp is equal to 4.5 A by lambda square. And here the capital AA is equal to dE into dH, which represents the physical area of the aperture. I repeat the design equations of the horn antenna. Theta is equal to 2 tan inverse of d by 2l, that is equal to 2 cos inverse of L by tau, where L is equal to d square by 8 tau, and offer beamwidth of optimum flared horns are pi is equal to 56 lambda by dE degrees, and pi h is equal to 67 lambda by dH degrees. Here pi a is equal to half power beamwidth in E plane and pi h is equal to half power beamwidth in H plane. D is the aperture in E plane in free space wavelength, and dh is the aperture in H plane in free space wavelength. The directivity of horn is d is equal to 7.5 AA by lambda square, and power gain is equal to Gp is equal to 4.5 A by lambda square. Here AA is equal to dA into dH is equal to physical area of the aperture. Let us discuss now salient features of the horn antenna. The horn becomes small if the flare angle is small. Its radiation pattern is directive, the wavefront is spherical, mouth area is small, and its directivity is small. The horn becomes small if the flare angle is small, and in such a case the radiation pattern will be directive, and the wavefront is also spherical, and the mouth area is small and its directivity is small. The flare angle is related to the axial length. If theta is equal to 15 degree, when 1 by lambda I by lambda is equal to 50, the beam width is 23 degree and the directivity is 120. The directivity of pyramidal horn is more as the flare is in more than one direction. Its directivity is not as high as that of the paraboloid, and this horn antenna is used as a radiator, and it is very easy to use with the waveguide. It is used as a primary antenna for the paraboloid, and the gain of the conical antenna is optimum for a given slant length of flare L, and d is equal to 3 by lambda whole power of half, where d is the diameter of the aperture. I repeat the salient features. The horn becomes small if the flare angle is small. The flare angle is related to the axial length. If theta is equal to 15 degree, when L by lambda is equal to 50, the beam width is 23 degree as well as the directivity is 120. The directivity of pyramidal horn is more as the flare is in more than one direction. This directivity is not as high as that of the paraboloid, and it is used as a radiator. It is easy to use with a waveguide. It is used as primary antenna for the paraboloid, and the gain of the conical antenna is optimum for a given slant length of flare L, and d is equal to 3 by lambda whole power of half. Now, let us continue the salient features. Coming to the directivity for a lossless horn antenna, the directivity is equal to the gain, and it is given by d is equal to 4 pi AE by lambda square, where AE is equal to eta A into AA, 4 pi by lambda square into eta A into AA, where AA is the effective aperture in meter square and AA is the actual area or physical area in meter square, and eta A is the aperture efficiency which is given by AE divided by AA, and lambda is the operating wavelength which is expressed in meters. So, whenever we tell lossless horn antenna, directivity is equal to the gain, and it is given by dE is equal to 4 pi AE by lambda square. 4 pi by lambda square into AE can be written as eta A into AA, where AE is the effective aperture in meter square and AA is the actual area or the physical area in meter square. Eta A is the aperture efficiency which is given by AE by AA, lambda is the operating wavelength in meters. In the case of rectangular horn, AA is equal to dE into dH, where dE is aperture size in E plane, dH is aperture size in H plane. In the case of conical horn, AA is equal to pi d, where d is the aperture diameter. Whenever we tell the conical horn antenna, in that case AA, that is the actual or the physical area, is given by pi into d. D is the aperture diameter. If aperture efficiency is about 0.6, then the directivity is given almost equal to 7.5 AA by lambda square. When the aperture efficiency is 0.6, this dE is almost equal to 7.5 AA by lambda square. Now, coming to the applications of horn antenna, they are basically used at microwave frequencies where the moderate gains are sufficient, and they are used as feed elements, and they are often used in laboratories for the measurement of different antenna parameters. They are used at microwave frequency whenever the moderate gain is sufficient, and they will be used as feed elements as well as to measure the different antenna parameters. We use them in laboratories. Now, let us discuss about one problem related to the helical antenna. It is design a 10-turn helical antenna so that at the center frequency of 10 gigahertz, the circumference of each turn is 0.95 lambda, and if we assume a pitch angle of 14 degree, we need to find out the mode in which the antenna operates, the half power beamwidth and directivity in decibels. And this is actually operating in axial mode. And coming to the half power beamwidth, we can use the formula of half power beamwidth and find out, and the answer comes in the range of 36 degree. Similarly, the directivity expressed in decibels, it comes in the range of 15 degree after taking the formula of directivity and doing the substitution with respect to the parameters. This is about the discussion with respect to the horn antenna and the problem analysis with respect to the helical antenna. Let us now discuss about the reflector antennas. In the reflector antennas, there are many types. Coming to the flat reflector antenna, this is the plane, and this we call it as a reflector, which is a flat plane, and there is a feeder element here, driven element, and the signals that are being generated by means of this driven element is getting reflected from this reflector in this fashion. Similarly, there may be a pattern in which we can do the corner reflection. This is the plane of the reflector, and this is the point at which we use the feeder element, and the reflection happens at the corner sections with respect to the reflector. The next type, we have got curved reflector antennas. This is called as prime focus reflector, and this is called as Casagrana reflector. In the prime focus reflector, we have the reflector in the form of a parabola, which is having vertex at the center, and at a distance, at some distance, we locate the feeder element or the driven element, and this point we call it as a focal point. From this point, the signals that are being generated will be directed towards the reflector, and from the reflector they will be reflected, and all the reflections, they follow the same horizontal direction. In the Casagrana reflector, we have got double reflection here. I can tell that we are using a double reflection because there are two parabola reflectors here. One is called as main reflector, another one is called as hyperbola. Parabola and hyperbola, main reflector and sub reflector. This is the point at which we locate the feeder element or the driven element. From this, the reflection actually happens, and it actually first goes to the sub reflector. From the sub reflector, it goes to the main reflector, and then it takes the same direction with respect to the transmission. The same path for all the reflections will be maintained. This is with respect to the corner reflector antenna. This is the top view of the corner reflector, and this is the case in which the wave incident at 90 degree corner reflector, it reflects back in the same direction. Wave incident at 90 degree, it reflects back in the same direction. One more view with respect to the reflector antenna has been given here. This is the prospective view, and this is the Y grid arrangement. This is the slide which is actually giving the images for the corner reflector antennas. These are actually the 3 images for 90 degree corner reflector antenna, and these are the 5 images for 60 degree corner reflector antenna. These are again images for corner reflector antennas. There are 7 images for 45 degree corner reflector, and there are 11 images for 30 degree corner reflector. Thus, finally, what is the conclusion that we can make is number of images are actually dependent upon this angle, and the formula is given by 360 by alpha minus 1. Depending on this alpha value, we get the number of images here. The number of images is equal to 360 degree divided by alpha minus 1. This is the reflector that we need to learn with respect to the syllabus of the microwave and antennas. The type of the antenna, reflector antenna, is parabolic reflector. Let us have an understanding of this parabolic reflector antenna. This is a reflector antenna which has the shape of the paraboloid, and it employs the properties of the parabola. As you can see here, this is in the shape of a parabola, and as well it employs the properties that are used by the parabola. Same properties are applicable for this parabolic reflector as well. The parabola, it is a plane curve which is obtained by the locus of a point which moves so that a distance from another point called the focus plus its distance from a straight line called directrix is constant. It means this parabola, it is a plane which is obtained by locus of a point. This is the locus of the point which moves so that a distance from another point, that is, this is the focus point. From this distance whatever you take here, that is, this is the FP, and whatever distance that is been covered in the horizontal direction PP bar, FP is equal to PP bar. FP will be equal to PP bar. FP plus PP bar, that is equal to FQ plus QQ bar plus FR plus RR bar. Similarly, this is the F, right, Fs plus Ss bar equal to Ft plus Tt bar. It means the locus of a point from its distance from another point called the focus plus its distance from a straight line called directrix will be constant. This is the directrix, PP bar is the directrix. A paraboloid is a three-dimensional surface which is obtained by revolving the parabola about its axis. This paraboloid is called the parabolic reflector or the dish antenna. This can be called as a three-dimensional surface because it is obtained by revolving the parabola about its axis. We are revolving the parabola about its axis. Coming to the geometry of the parabolic reflector, here AB represents the, this AB represents the axis of the parabola, and CD, this CD represents the mouth diameter, and AF represents the, this AF represents the focal length, A represents the vertex and F represents the focus, and CAD represents the parabola. The line CD is nothing but directrix, and AF by CD, this AF divided by CD we can call it as aperture of the parabola, and this is how the radiation pattern of the parabolic reflector antenna will be. Okay, this is about the reflector antennas, and mainly we are discussing about parabolic reflector antenna, how actually the construction of this parabolic reflector will be done and what are the dimensions with respect to the parabolic reflector. Thank you.